All right. Now today we're actually going to look at this compound over here. When I have a benzene ring, that is actually bonded, to an OH group. Okay. This compound here is given the name, this compound over here is given the name phenol. Okay. So it becomes again phenol. When you have an OH group bonded to a benzene ring, it becomes phenol. Okay, so again this becomes part, it's the main functional group, so the name changes. Okay, just as a carboxylic acid jab hoti thi, it became benzoic acid. This guy is known as phenol. Okay, now OL is for the OH group, and the phen is basically comes from the fact that this is a phenyl group. Okay, so that's phenol. Now my question is, do you think it's more reactive or less reactive than benzene? Phenol is much more reactive than benzene. All right. And we'll see why. All right. So the reason why it's much more reactive than benzene can be illustrated over here. All right. Now there's two things at play here. Now you might think that, okay, it's less reactive than benzene because oxygen is more electronegative. Okay. That is true. Oxygen is more electronegative than benzene. Okay. So oxygen does have it has a negative inductive effect. It's withdrawing electron density from the carbon. It's much more electronegative than the carbon. So therefore it's withdrawing electron density from the carbon. But at the same time, one of the oxygen lone pairs that resides in a p orbital can overlap with the rest of the benzene ring. Okay, can overlap with the rest of the benzene ring. So this effect is known as the resonance effect. Okay, this is known as resonance. If you guys remember, resonance was just delocalization of electrons. So initially benzene में क्या था? बेंजीन में आपके पास सिर्फ 6 इलेक्ट्रॉन थे रिंग के अंदर. बेंजीन में you only had 6 electrons in the ring. बेंजीन के अंदर you only had 6 electrons in the ring. When benzene is bonded to phenol or an OH group in phenol, when benzene is bonded to an OH group, what happens is that the lone pair from the oxygen atoms arrange itself in such a way that the lone pair that's in the p orbital in the oxygen atom delocalizes into the ring. It delocalizes into the ring. Okay. So what we have is, yes, oxygen is withdrawing electron density. That's called induction, right? It's a negative inductive effect. It is a negative inductive effect. Oxygen is withdrawing electron density. However, it's providing way more electron density because of the overlap of the p orbital that has the lone pair and oxygen with the rest of the ring. Okay, so over here this is called the resonance effect, and in this particular case, in the case of phenol, this resonance effect outweighs the inductive effect. Okay, and because of this delocalization of the lone pair of electrons, from the p orbital, okay, or the delocalization in the p orbital, right, of the oxygen atom, because they're delocalized into the ring, it means that as a net effect the ring has much greater electron density, making the ring far more reactive towards electrophiles. All right, so what happens in phenol is this, right? What happens is that even though so the inductive effect, again, the inductive effect is basically oxygen is more electronegative, right? Its nucleus attracts electrons more strongly. So it is withdrawing electron density away from the ring. That's the inductive effect. That's negative induction. It's taking electron density away, electron withdrawing. But at the same time, one of the lone pairs, the other lone pair is not in this plane, it's perpendicular to this plane. But one of the lone pairs, or one of the p orbitals, arranges itself such that it delocalizes into the benzene ring. So over here, for example, let's say if you had a benzene ring, right, it had 6 electrons, whereas over here, because of the lone pair, one of the p orbitals, okay, the lone pair in one of the p orbitals in the oxygen atom has delocalized into the benzene ring. So now what you have is, instead of 6 electrons in this ring, you have this delocalization all the way from the oxygen atom over the ring. So now you have 8 electrons. You have 8 electrons in the ring, making phenol much more reactive towards electrophiles. Okay. All right. So we can say that phenol is much more reactive, okay, much more reactive towards electrophiles than benzene is, okay, because 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 the lone pair okay, in the p orbital, okay, of the oxygen atom, okay, or rather because the lone pair of electrons, in the p orbital of the oxygen atom delocalizes into the benzene ring. Okay, what that means is now there are 8 electrons in the pi delocalized ring in phenol. Okay, versus what, 6 in benzene. Okay, which makes the phenol much more reactive, right? So there's an increase in electron density in the ring, making benzene much more reactive, or making phenol much more reactive. Okay, making phenol much more reactive. Again, if the increase in electron density means that it attracts electrophiles more strongly. All right, so now let's compare the strength of the CO bond, right? So now the CO bond in phenol, right? The CO bond in phenol is much stronger, okay, than in than a regular CO bond than usual, because of what? So the CO bond is much stronger than usual because of this delocalization of the lone pair in the p orbital on the oxygen atom, right? What you have is, between the carbon and the oxygen atom, you have the sigma bond, but you also have this partial pi bond, right? Because of the pi delocalization, now you have an 8 electron pi delocalized ring. So there's partial pi bond characteristic to the CO bond over here, right? So what happens is that because of the CO bond is much stronger than usual because of the overlap, okay, because of the overlap between the p orbital, or rather because of the delocalization, of the electrons of the lone pair, okay, of electrons in oxygen, right, or on oxygen. And the reason why is because when you increase electron density, right, between the carbon and oxygen atom, right, you increase electron density between the carbon and oxygen atom, which means that you increase electrostatic forces of attraction between the nuclei and the shared pair of electrons. Okay, so what that means is that the CO bond in benzene is actually relatively unreactive, or in phenol, sorry. The CO bond in phenol is relatively unreactive. So over here, the ring is much more reactive. Because of delocalization of electrons, okay? But the CO bond doesn't break very easily. The CO bond is unreactive, okay? The benzene ring is much more reactive because of the delocalization of electrons, but because of the delocalization of electrons, right, what happens is the CO bond is much stronger because there's more electrons present between the carbon and the oxygen atom, so stronger electrostatic force of attractions, which means that this CO bond doesn't break very easily. Okay, making this so the CO bond in phenol is relatively unreactive. Okay, doesn't break easily. So we've already seen how phenol is much more reactive. Makes the benzene ring much more reactive towards electrophiles than you would just see in benzene because of the delocalization of the lone pair of electrons in the p orbital on the oxygen atom into the benzene ring, which increases the electron density in the benzene ring, and it makes it attract electrophiles more strongly, making it more reactive, making the ring more reactive. At the same time, the CO bond in phenol, because of this delocalization, there's greater electron density between the carbon and the oxygen atom in the CO bond, right? And if there's greater electron density, it means that the CO bond doesn't break. So unlike alcohols, which undergo nucleophilic substitution, alcohols में क्या होता था? For example, अगर bromine या chlorine के साथ आप react करते थे, HBr या HCl के साथ, HBr या HI के साथ, sorry, the halide would actually replace the OH group, right? That would substitution would take place. The CO bond would break. In the case of phenols, that doesn't happen. Okay, in the case of phenols, that doesn't happen. The CO bond doesn't break very easily because it's much stronger than usual due to this delocalization. So because the CO bond doesn't break, you can't really, nucleophilic substitution doesn't take place the same way it does for alcohols. Okay, so the ring becomes less reactive, but the CO bond becomes, the ring becomes more reactive because of increase in electron density, but the CO bond becomes less reactive, and this OH group doesn't really break off. All right. So phenols are not alcohols. Okay. The name of the functional group is actually called phenol. Phenol itself is the name given to this functional group. Okay. So this is actually the functional group. Okay. It's different from alcohols. All right. And just like the alkyl groups, okay, phenol is also a 2,4 directing group. Phenol is also a 2,4 directing group. Okay. All right. So when we look at phenol over here, okay, we can say that the name of the functional group itself is phenol. All right. It is a 2,4 directing group. It is a 2,4 directing group. Okay. And it is also an activating group. It is 2,4 directing, and it is an activating group. Again, an activating group is one that makes the benzene ring more reactive towards electrophiles. Okay, so carboxyl groups, for example, are deactivating groups. They make the benzene ring less reactive towards electrophiles. Okay, phenol is an activating group. Let's look at the bromination of phenol. This reaction will show how phenols are much more reactive. So if I take phenol over here, okay, and I react it with bromine, okay, this is bromination of phenols, okay, I actually don't even need to provide any heat. Okay, just like in the case of methyl benzene, because phenols are more reactive than benzene. And I don't even need a catalyst here. So what happens is that phenol is so reactive that what happens is that you get 3 bromines being substituted onto the benzene ring. 3 bromines substitute onto the benzene ring directly. Okay, so you have Br, Br, and Br, like that. Okay, so it's super reactive. Again, this reaction, because the ring is so much more reactive towards electrophiles, this reaction can happen at room temperature without the presence or in the absence of a catalyst. Okay, and what you end up forming is, as a byproduct, is 3 moles of HBr. Okay, now this reaction, what happens is that you actually form this product over here is called 2,4,6 tribromo phenol, right? So obviously the main functional group is phenol, so that's given the carbon number 1, right? And then you have bromine on carbon 2, carbon 4, and carbon 6. So the product of this reaction is 2,4,6 tribromo phenol, and this is a white precipitate. So the observation in this reaction is that you see the red okay, what you see over here is you have bromine aqueous. Okay, you have bromine aqueous, which is like an orange brown solution. Okay, that's decolorized. The brown solution is decolorized, okay, to form a white precipitate. So in this reaction, the observation is decolorization of aqueous bromine and formation of white precipitate 2,4,6 tribromophenol. So this reaction exemplifies how reactive phenols are, okay, or how reactive the benzene ring is when a phenol functional group is present. The next reaction that we are going to look at is the nitration of phenols. The nitration of phenols. Okay. Now what happens in the nitration of phenols? Well, in the nitration of phenols, what you have is this. You're starting with a phenol. Okay, you're starting with a phenol. And now, does anyone remember the reagent that we use for nitration of benzene? So for the nitration of benzene, we had to use concentrated nitric acid as our reagent. We used concentrated sulfuric acid as a catalyst, and we had to heat around 50 degrees Celsius. For the nitration of benzene, however, for the nitration of phenol, however, you don't have to heat it at all, and you don't have to use a catalyst either. You can just use dilute. You can use dilute nitric acid as your reagent. It doesn't have to be concentrated, and you don't have to use a catalyst either. Just dilute nitric acid will work. Okay, because it's so much more reactive, and our products, we get two different products over here because it's 2,4 directing. All right, either you're going to get the nitro group on the second carbon like this, or you're going to get the nitro group on the fourth carbon like that. Okay, and again, because phenol is the main functional group over here, the first compound is called 2-nitrophenol, and the second compound is called 4-nitrophenol.